Hello everybody, welcome to lesson 2 of unit 6, and in this lesson we're going to cover class templates from chapter 13 and the vector class in chapter 21. Specifically, we'll discuss how to define a class template and then talk about how to use the standard template library class vector. Vector is a great class to examine because it is both a class with dynamic data and a class template. Of course, your learning objectives for this lesson will be for you to be able to define your own class template and to use the standard template library vector class, as well as use the iterator defined for the vector class. Now don't worry if you don't know what an iterator is, we're going to get into that later in the chapter. The function template was first introduced back in unit 2. It allows us to write a generic function which can be used with different types of parameters. And here's an example of one such template and its usage. Don't worry about syntax now, we'll get into that in a bit. During compilation, the compiler automatically instantiates a version of the function template. Each occurrence of the type parameter is replaced by a specific type in a function call. Notice how we only had to define the function template once, but we can use it for multiple classes. The beauty here is that with a minor amount of code overhead, we achieve a significant amount of code reuse. This template will work for any class that supports the plus operator. The main takeaway here is that the generic functions promote code reuse. A class template is similar to function templates. It allows us to write a generic class which can be used with different types. One of the classic examples of a generic class is a class handling a list of items, the so-called collection class or container class. The array class in Java is a collection class. It can hold a list of integers, strings, clock objects, and whatever else you want to throw in there. This is the arraylistType class example from our textbook, and it can be used to hold a list of items of any type. It has a pointer data member which points to a dynamic array. It has a default constructor, a copy constructor, and of course a destructor since we are dealing with dynamic data. And it also has an overloaded assignment operator so we can copy data over from another list. And if you remember from the last lesson, we need all of those things when we're working with a class that has dynamic data. The class also provides functions to access and mutate the list, and some additional utility functions. Pay attention to places where the type parameter elemtype is used. It's used when you need to reference an item or the name of the class. Here's the implementation of some of the member functions. The member functions of a class template are considered to be function templates, and therefore this syntax is similar. Be aware that the name of this class is arraylistType together with its type parameter, as you can see here. The retrieveAt function is the member function to retrieve one element at a specific index. The element will be sent back through a reference parameter. And here's the driver code to utilize the arraylistType class. As you can see here, you must specify the parameter type when declaring an arraylistType object. So here you can see we're specifying that this one is going to store ints, and here you can see that we're specifying that we're going to store strings. Now you only have to do this when you instantiate the class, because after you instantiate it, you'll be referencing it from the alias. So in this case, we got string list and we got int list, and here we're just using the name that we've given that object. Let's look at another example of a class template called myPair. One difference is that it couples a pair of values which may be of two different types. You can see that specified as T1 and T2. You can see that it also has two private data members to store those values, a constructor, two accessor functions, two mutator functions, and it also has an overloaded output operator. For practice, I highly encourage you to attempt to provide the implementation for this class. You'll need to provide the constructor, the getter and setters, the swap function, the output operator, and finally the driver code to exercise your new class. And it may seem like a lot of work, but trust me, you'll learn much more if you do this than if you just watch the videos. The myPair class is similar to the pair type in the C++ library. Pairs are a common structure for many applications. For example, think about coordinates on a standard XY plane. As you can see here, it's defined in the header file utility. And it is, in fact, a template, and it's also a struct. Since it's a struct, you can directly access the public members. This pair class provides an easy way to bundle two values. The string class we've been using is also defined through a class template. It's defined on top of a class template basic string. This class template is instantiated to define a string and other similar classes, although you almost exclusively always see it used in the standard string instantiation form. The point of these examples is just to show you that there are many features of the language that you've been working with already, and that these features are in fact class templates. Now that you understand what function and class templates are, it's time to introduce you to C++'s standard template library, or STL as it's known. This library defines container classes, iterator classes, and some commonly used algorithms. The container and iterator classes are class templates. Iterators are classes that act like kind of pointers. They are used to access items in a container class. Finally, the algorithms are defined using function templates so that they can be used to work with data of many different types. Let's start with the container classes. There are different types of container classes, but for the purpose of this lecture, we're only going to cover sequence containers. Sequence containers are containers whose items can be accessed through its index. Of the 5 sequence containers, we're going to only look at the vector class, as it is a commonly used STL class. It behaves just like the arraylist class in Java, which we covered extensively in Cs225. Vector is a class template, and it has dynamic data. Therefore, it's a great example to examine. The vector class is defined in the header file vector. Here are examples to declare an int vector and a string vector. These two declarations invoke vector's default constructor. However, vector also provides a copy constructor, a constructor with a capacity parameter, and a constructor to easily create a vector object holding n elements of the same value, as well as many others. The vector class provides many member functions. Here are 3 typically used mutator functions: to append, to delete the last element, or to clear a vector object. There are 3 size-related accessor functions. Size returns the number of elements in the vector, capacity returns the current capacity, and max size returns the max capacity in theory on a computer system. You can write a simple program to test those 3 size-related functions. Here we create an int vector and add 100 items. After that, we print out the results of those 3 functions. On my machine using Visual Studio 2019, you can see the following results. Its size is obviously 100 because we filled it with 100 values. The capacity is based on how the vector class chooses to grow its capacity. It's expected that there is some form of exponential growth, such as doubling every time it gets filled. The max size is a theoretical cap on the size of the vector on my machine and compiler. Here you can see the results based on running this program on an online GNU compiler, and you can see clearly that there's a huge difference in the theoretical max size. The capacity will always be greater than or equal to the size. Once the current capacity of a vector is reached, the system will automatically expand the capacity by reallocating its storage space. This is just like ArrayList in Java. In theory, a Java ArrayList object or a C++ vector object will never be full. The max size is a theoretical cap on the size of a vector. Generally, you shouldn't use capacity or max size in your program. To use vector and the standard template library efficiently, you need to understand iterators. As I stated earlier, an iterator is a pointer kind of class. Iterator objects can be incremented or decremented, dereferenced, and compared against another iterator. The standard template library uses iterators to access elements of containers. Additionally, you can use iterators as function parameters or the return type. Using iterators makes the standard template library algorithms more generic because the algorithms will work for any containers, including the ones you build, provided you define proper iterators for them. Finally, it's also more efficient. By passing and returning iterators, you don't need to copy a whole container object, just like the difference between a reference parameter and a value parameter. Let's look at an example program. We declare a vector of int and add 5 values to it. This is how we declare an iterator object that can point to elements of this vector. Notice the double scope resolution operator. Here we are declaring a vector of type int, and then we're declaring an iterator of that type. And here is where we'll print the contents of this vector. The iterator will point to the first element because of the call to the begin function, and we'll then increment the iterator over each loop until it reaches the end of the vector as specified by the .end function. At each step, we dereference the iterator to retrieve the item at that location. You can also rewrite the for loop like this to express that the iterator hasn't reached the end of the vector. Notice here we're using the less than sign instead of the not equal to operator. That's because the .end will actually return an iterator past the last value. So if we just do less than, then that will make sure that we get the last value in the vector. In addition to the mutator functions we already mentioned, the vector class has several insert functions which allow insertion into the middle of a vector using iterators. This 2-parameter insert will insert a value at the position identified by the first parameter, which is an iterator. This 3-parameter insert function can insert multiple copies of one value into a vector starting from the position identified by an iterator. Both functions return an iterator pointing to the first of the newly inserted elements. Okay, time for a pop quiz. Given the following code, which statement is the correct one? Do we need to save the returned value of insert in line A? Right here. So our options are A, no need, may take the assignment part out. B, we need this returned iterator value for the next call of insert. C, we must save or use the return value of the insert function of a member class. Or D, we must save or use the return value of a function, any function with a return value for that matter. So go ahead and think about it and pause the video, and I will give you the answer in a second. Okay, did you pick answer B? I hope so. When you modify a container using an iterator as the position, you may invalidate the iterator due to underlying changes in the container. We can insert 300 2 times on the last insert without saving the returned iterator because we aren't using it again to access the container. The takeaway here is that you must exercise caution using iterators in this way. Now, given the same block of code, what will be printed out? Go ahead, pause the video and see if you can come up with an answer. Okay. Did you get answer D? If you compiled and ran the code, did you understand why? Let's take a look at it. So here we're creating a vector with 100 in it 3 times, okay? So that we obviously know that we are going to have to see 100 3 times in our answer. Then we create an iterator. Then we set our iterator to the beginning of the vector, okay? And then we insert at our iterator 200. So that means we are going to insert our iterator before the first element, and then we're going to return a reference to that. So that means we have 200 in front of our 3 100s. So right there you can tell that at this point it's either option A or D, because 200 is behind the hundreds and here 200 is behind the hundreds. Then we're going to add our iterator 2 times the number 300. So 300 is going to go into our vector twice at the position of our iterator. So that means it's going to go to the front. So that gives us answer D, because 300 is in front of 200, which is in front of our other hundreds. And then the rest of this is just iterating through it, printing out the result. So hopefully you got all that. All right, one more question for you. Insert has yet another overloaded option, where the first parameter is the position and the second and third parameters are iterators or pointers that point to the start and stop of a range of values. So given this knowledge, what will be printed? Take your time, trace the program, and see if you can figure it out. Go ahead and pause the video and I'll give you the answer in a second. Did you get answer C? If not, don't worry about it, because we're going to walk through it. We start with our initial vector and we set our iterator to the beginning. We then create another vector and insert it using a range from beginning to end at iterator plus 2, which leaves us with this. We then create an array and insert a range of values from the first element to the first element plus 2 at the beginning of the original vector. Remember that the last parameter of the range is not inclusive. So in this example, we will only be retrieving 2 values from the array and not 3. And there you have it. When we call insert on a vector, memory reallocation may happen if the current capacity has been reached. That means a new, larger dynamic array will be allocated. Items in the current dynamic array will be copied over, new elements inserted, and the old dynamic array will be deleted. Now the iterator doesn't point to a valid location of the vector object and therefore becomes invalid. This is called iterator invalidation. And this may happen to iterators pointing to, before, or after the point of insertion. Because of iterator invalidation, we should reposition an iterator after an insertion by saving the returned value of an insert or calling vector.begin or a similar function. In addition to the insert function, there are functions to delete items from the middle of a vector. This one parameter erase will delete the item pointed by the iterator by shifting elements one position to the lower index end, i.e. towards the beginning or towards the 0th index. It returns an iterator pointing to the item after the erased one. This 2-parameter erase will erase all items in the range defined by the 2 iterator parameters. Finally, here are some functions providing access to items stored in a vector. You may access one element through the @, function or by using the subscript, just like how the string class works. We also have the front and back functions, which return the first and last element respectively. Remember, these functions are for the vector class and not for iterators. The two things go hand in hand, but it's important to remember that they have different member functions. Always reference their implementations if you're in doubt. C++ 2011 also added a member function called data to return a pointer pointing to the underlying array that's storing the actual data, but you should use this with caution. The iterswap function is useful when working with iterators. For example, given this code, the resulting vector would be, and another important thing to remember is that the .end function gives you an iterator that points to the position after the last element. And I know I mentioned this previously, but I wanted to reiterate it, get it? That the last element is whatever is at the end, and the .end function points to an iterator that happens after it. right? So it won't give you the last element. Like beginning will give you the first element. The last element is actually the end function minus 1. So if you want the last element of a vector, again, you need to decrement it by 1. For the final section of this lecture, we are going to practice problem solving using the vector class. Given a list of numbers in a vector, rearrange them so that all the even numbers come before all the odd numbers. Other than that, the numbers can be in any order. And here are some test cases. I want you to pause the video here and think about the problem and how you would approach it. And we're going to cover 3 different approaches, but I want you to exercise that gray matter and actually try to come up with a possible solution. Don't have to code it or implement it. I just want you to think about your algorithm. How would you go through solving this problem, right? So go ahead and pause the video, think about that, and we'll get started on the next set. So let's look at the 3 different approaches or 3 different algorithms for solving this problem and compare their efficiency in terms of execution time and memory usage. The first approach could be to use a variation of the selection sort. We loop through each element, move an element to the front of the vector if it's even, otherwise do nothing, like this. This appears to be simple and a straightforward approach. And it also seems to be a simple one-loop solution. However, inserting an element into the front of a vector requires a loop inside of the insert function to shift all the elements one position towards the higher index n. That means an insert here actually requires n times n steps, with n being the size of the vector. Therefore, this algorithm requires n squared steps in time complexity. A second approach will use another vector as a helper. Loop through each element in the original vector and copy this element to the tail of the helper vector if it's even. Once all even elements are copied over, a second loop will copy all odd elements to the helper vector. This approach requires another vector which needs to hold n elements at the end. Compared to approach number 1, this means extra memory space for n number of elements. It needs to scan the vector twice, but there's no shifting. And adding an item to the tail doesn't involve any shifting either. We don't need to remove, only copy an item from the original vector to the helper. So overall, the time complexity is n number of steps, or it's linear. This approach is probably the most straightforward and easiest to understand. A third approach uses iterators. 2 iterators are used to point to the first and last element. We'll loop through the vector when there is still elements in the range of those 2 iterators. We'll look at our first iterator, and if it's even, we'll increment it, but if it's odd, we'll look at the last iterator. If the last iterator is odd, we'll decrement it, but if it's even, we'll swap the values of the first and last iterators. We'll then move both iterators towards the center of the vector by 1 position and repeat. And you can, hopefully you're watching the visualization. If not, let's watch it again. This approach scans the vector only once. It doesn't shift items or use another helper vector. The time complexity is n without the extra memory space as needed in the second approach. In summary, we covered 3 different techniques for handling the even and odd problem. You can see how if you approach a problem differently, you can have a big impact on what you need to solve the problem. At this point in your education, you should not only be able to build a program that works, but you should also be able to start to analyze the efficiency of your code. And I hope walking through this problem gives you a little bit of extra practice in thinking about the problems. So in summary of the whole lesson, we introduced the class template, and we talked about how this allows us to write generic code which promotes code reuse, just like the function templates. We also looked at the vector class from the standard template library as an example of a class template and a class with dynamic data as well. The vector class is commonly used, is a commonly used container class in C++, while the iterator concept is essential to use the container class to their full potentials. And that's it for this week's lesson. Hopefully you've done some practice, or I hope you do some practice after watching the videos, because more practice never hurts.